Four couples are at a party. Four people of the 8 are randomly selected to win a prize. No person can win more than one prize. What is the probability that both members of at least one couple win a prize? Alright, well I'm going to show you a couple different ways to do this problem, mainly because there's an easy way and there's a hard way. And when I first did this problem, I chose the hard way, not realizing it was the hard way. And I got the wrong answer and I couldn't figure out why it was wrong. And so I learned something by getting it wrong, and so I wanted to share that with you. Alright, so let's start with the easy way. So the easy way is to use something called complementary counting. Okay? Complementary counting, or in this case it's probability, but essentially we count what we don't want. So the probability is the number of desired outcomes over the total. And the total number of ways that these prizes could be distributed is pretty simple in this case, because we're going to choose four. We're going to assume. I'm going to assume in this case the order that order matters. Okay, so maybe these prizes are, one's a big screen TV, and maybe one's a gift certificate for some fancy restaurant, and maybe another one is a new toaster. Okay, so they're different prizes. So if that's the case, we have 8 people total, and so we would have 8 choices for the first person to win the prize, to win a prize, and then we would have 7 people left. We're assuming that no person can win more than one prize. And then we'd have 6 people, and then 5 people. Okay, and that would give us the number of ways that we could distribute the prize among 8 people with no restrictions. Okay, and the desired outcome in this case is to have at least one couple win a prize. And the complement of that desired outcome is that there's no couples that win a prize. Okay, so each of the people who win prizes come from different couples. Okay, so, and we only have 4 couples, which means that one person from each couple has to win a prize. So in this case, I could sort of draw a little diagram here. So here's our couples. Okay, and we'll couple them with a little circle. Okay, so those are our couples. And so we have 8 choices for the first person. Okay, so it doesn't really matter what couple they come from at this point. All right, and remember, we're counting the complement, so we're going to count how many ways we can distribute these prizes so that all 4 prizes go to different couples. Okay, so we have 8 choices for the first, and then we basically have eliminated one of the couples. All right, so now we're down to really 6 people. All right, so we have 6 choices for the second, and now we eliminate 2 couples, and then we have 4 people left. So then we have 4 choices for the third prize, and then finally we've eliminated 3 couples, so we're down to just 1 couple, and so we have 2 choices for the 4th person to win a prize. Okay, and if we write that probability, that's equal to 8 times 6 times 4 times 2 over 8. Got a cat on my on my laptop here. Okay, 8 times 6 times hang on, sorry. The cat distracted me here. So our total is 8 times 7 times 6 times 5. Okay, and we can cancel some of these things, and we end up with 8 over 35. Now that's the probability of the complement. Okay, and we know that all the possible outcomes, if we added the probability of all the possible outcomes, they would add up to 1. So if we take 1 and subtract the probability of the outcomes we don't want, 8 over 35, oops, 35, and then we end up with, so this is 35 over 35 effectively, so we end up with 27 over 35. So, so that's the answer, and that's the easy way to do the problem, is by complementary counting. And so I'm going to show you another way to solve this problem, and I can show you where I went wrong when I first when I solved it. So I'm going to actually put that in another video because I'm afraid it'll run over the time limit here. So this is the answer, 27 out of 35, and it's pretty simple, pretty straightforward to do it by complementary counting.